Good day everyone, my name is Maiden Pabian and my topic is about roots. The first one is the root hair. Root hair is a hair-like growth of a plant root and absorb water and minerals from the soil. This is the reason why water is so important in plants' development. Water moists the soil and help ions to move freely from one place to the other, changing properties them easily. Next, the main root. Phloem. The phloem is the living tissue that carries organic nutrients, in particular, sucrose. Sucrose is a kind of sugar that to all parts of the plant were needed. Xylem. The basic function of xylem is to transport water from roots to shoot and leaves. It is located at the center of the root, which makes it easier to supply water to every part of the plant. Next is apical meristem. It's found at the tips of the plant. Both of the tip of the shoot and the root is a region of active dividing cells. Cell division means root growth and expansion. And the last one is root cap. Root cap contains statocytes which are involved in gravity perception in plants, as well as the protection of the apical meristem. And we have two classes of nutrients are considered essential for plants. The first one is macronutrients. They are the building blocks of crucial cellular components, like proteins and nucleic acids, as they are required in large quantities. Nitrogen, phosphorus, magnesium, and potassium are some of the most important macronutrients. Carbon, hydrogen, and oxygen are also considered macronutrients because they are required in large quantities, but they represent the non-mineral class of macronutrients. And next one, micronutrients. Micronutrients include iron, zinc, manganese, and copper are required in very small amounts. Micronutrients are often required as cofactors for enzyme activity. And also, we have two types of root systems, taproots and fibrous roots. The taproot system. Typically, a taproot is straight and very thick, is tapering in shape, and grows downward. The taproot system found in most dicotyledonous plants, and also called the primary root. Example, carrots. And the last one, fibrous root system. Fibrous root systems are usually formed by thin, moderately branching roots growing from the stem. Fibrous root can be observed in most monocotyledonous plants and other plants like a fern, and also called an adventitious root system. For examples, grasses, rice, and corn.
Okay, so with the exception of carbon and oxygen, which are supplied as carbon dioxide from the air, terrestrial plants generally take up nutrients elements from the soil. So, so the nutrients, no, will take, no, by the plants through the root system. So the soil and the root system have this deep, no, connection. Okay, so soil is a very complex medium because it consists, no, of solid phase and the inorganic rock particles and organic material. No, so the organic materials are contained, no, with dissolved solutes and a gas phase generally in equilibrium with the atmosphere. So inorganic solid phase of soil is derived from parent rock that is degraded by weathering processes to produce particles of varying size. So you can see, no, in this picture we have the different layers and hidden, no, in a horizon. So we have the organic topsoil, subsoil, substratum, and the base is bedrock. So this now, so this is now the soil profile. So we have there the O horizon, the A, E, B, C, and R horizon. So you will notice, no, different layers or horizon of soil. So we have the A, no, the O, A, E, B, C are horizon. So these layers have different, no, in texture, different in structure, different in colors, and also, no, different in nutrient, no. So the horizon that sits on the surface, which is the O layer or the O horizon, no, and the two layers below the O layer and are A, E, and B horizon. So these layers are known as your true soil. No, this true soil, no, are contained most of the chemicals and biological activity that helps the plant, no, grow. So you can see here, no, kung nababasa nyo, itong layer na to, yung A horizon, which is the layer that have mineral soil, no, and organic matter. So while the E horizon, these are the consist of silicates, and lastly the B horizon consists of iron, no, iron, clay, aluminum, and organic compounds. So the C and R horizon, basically these are the large unbroken rocks, no, and the R horizon, this is the soil or the base, no, of the soil profile, which is the bedrock. Okay, it's said that the soil as a nutrient reservoir, no? So soils now vary widely with respect to composition, structure, and nutrient supply. So in the different types of soil, no, they may vary in composition, structure, and nutrient supply, no, that needed by the plant. So some soil, no, or the types of soil have walang gaanong nutrient, no, na pwedeng makapagbigay, no, ng na kailangan ng ng halaman. So meron din mga composition or meron din mga soil na needed doon sa specific weather or season and needed doon sa specific na halaman. So merong mga halaman kasi na hindi pwedeng may mga soil na hindi pwedeng tamnan, no, ng halaman. So pwedeng hindi mabuhay or pwedeng mabuhay man pero hindi gaano katapa, no, yung halaman, which is also pwedeng mamatay, no, kung hindi gaanong madaming nutrient yung lupa na ilalagay doon sa halaman. Organic and inorganic particles, no, are now called colloids. So the soil colloids, no, retain nutrients for release into the soil solution where they are available for uptake by roots. So thus, the soil colloid serves to maintain a reservoir or reservoir of soluble nutrients in the soil. So that's why tinawag na reservoir, no, ang lupa. So next, so we have the different kinds of soil, no? So and also the significance of this, no, may also different. We have the sand, silt, and clay soil. So ito na yun. So nakikita nyo sa likod ko, no, sorry, ito na yung mga apat o yung halimbawa ng soil. We have sandy, slate, and clay, no, and loam soil. So meron silang kanya-kanyang specific, no, structure. Meron din silang iba-ibang composition. Meron din silang iba-ibang nutrient supply. So merong mga lupa na hindi gaano maraming nutrient supply. So meron din mga lupa na madami na supply, no, ng nutrient. So there, no, that's a classification of soil particles. So the loam soil is the mixture of 40% sand, 40% silt, and 20% clay. While the sandy soil contains less than 50% silt and clay, while a clay soil contains more than 40% clay particles. Next, so sandy soil. Sandy soil, no, is large, no, particles, and these sand soils are light and pretty to touch. And also, more often, no, sandy soils have low or less nutrient, and some sand soil are often acidic. So both water and fertilizer have tendency to leach out of the soil. So before the plant can utilize them, the nutrients in the water are sand soil or the sandy soil. So we have the advantage, or disadvantage of sandy soil. So as you can see, in my background, that's the example of sandy soil. So the advantage is sandy soil warm up quickly in the spring. So the disadvantage, so the sandy soil dries out quickly in the summer. Nutrients and water often leach away, especially with rainfall. And sandy soil are more often acidic. So how will you manage this sandy soil? So sandy soil is good for growing vegetables because it has good drainage. It warms up well. Unlike clay soil, it doesn't hold its nutrients. So gardeners must add additional components throughout the season. And you can add compost, manure, or grass clippings as a start, and this can improve a sandy soil. So this is how you will manage sandy soil. Is the clay soil. Clay soil, are the heaviest type of soil and are often considered the hardest to work with because they hold on to water and often take longer to warm in the spring. So the soil compaction and cracking is also a big risk of clay soils. Ultimately, this doesn't just look ugly, but it also keeps plants' roots from breaking through hard layers of clay. But unlike sandy soils, clay soils are rich with nutrients. With clay soils, nutrients are stored for much longer and have tendency not to leach away. So compared to the sand soil, bago pa ma-take up ng halaman, wala na yung nutrient, wala na yung water. While this, clay soil, the ability to store much longer and have tendency na hindi mawala. So we have also the advantage and disadvantages of this clay soil. So they are clay. So the advantage is clay soil hold on to nutrients so that the plants has the food it needs. So great for growing things that need a lot of water. The advantages, clay soil holds onto water, slow to drain, and it also slow to warm in the spring. It also compacts easily and tends to be alkaline or base. Manage the clay soil, toughest types, toughest type to manage, but with the right management techniques, you can improve the overall quality of your soil when it comes to turf. So aerating your soils each fall reduces soil compaction. So utilizing products that are rich in soil microbes will help your soil break down nutrient. So this picture is the sample, which is the permeability, allows water to easily absorb, kinds of soil, or types of soil. So here, in the first one picture, soil with high organic matter content and good structure permit water absorption. So it's very good in absorbing water. So while in this, in the middle picture, the hard packed surface, and plus impermeable subsoil, it prevent the water to absorb. Plus, behind me, these rock layers prevent water from soaking deeply into the soil. So it may not be absorbed, the water that needed by the plants if you layer. So this is the picture which you can easily know if the water will absorb or if the water will not absorb. Why the texture is very important? So the texture of a soil is very important because it determines soil characteristics that affects the plant, and also it may affect the plant growth. So a few of these characteristics are water holding capacity. Also these are now the three pictures. So we have the water holding capacity, permeability, and soil workability. So the water holding capacity is the ability of a soil to retain water. So most plants require a steady supply of water. It is obtained from the soil, which can also store the nutrients and the water for a long period of time. So that should water. Then while plants need water, they also need air in the zone. So that is with which air and water may pass through the soil called permeability. So the soil workability is with soil which soil may be filled and timing of the work. So the soil with a larger percentage of sand are easier to work than soils with a larger percentage of clay. So the clay soil tends to be tighter, making it more difficult to break up or cultivate. Sandy soil is looser, so it is also take longer for a clay soil to dry after a rain than a sandy soil. So this is the soil characteristic related to texture, and it shows these three pictures. So these are the example of the soil structure. We have there the granular, form, flatty, prismatic, massive, columnar, blocky, and single grain. So these are the category in soil structure. Tyndall effect, so the particles that are small enough to remain in suspension but too large to go into solution are called colloids. And the light scattering phenomenon known as the Tyndall effect. No? Tyndall effect is a distinguishing characteristic of colloidal suspension. So when the source of light or the light beam, and the true solution, light beam not visible, but in the colloidal solution, so you can see in the picture, the light beam visible because of this scattering of light or scattering particles. So a colloidal suspension, on the other hand, is a two-phase system. So it consists of a solid phase, the colloidal missile, and the suspended in a liquid phase. So the light scattered by the solid phase is responsible for the Tyndall effect. So this is the example on how to see the true solution, the colloidal solution, and the suspension. So it's called the colloidal suspension. Soil is the example of humus. So soil can also contain a colloidal carbonaceous residue. So this on my background is the example of a carbonaceous residue. So this soil is called humus. So humus is organic material that has been slowly but incompletely degraded to a colloidal dimension. So through the action of weathering and microorganisms. So it's in a good loam soil, the colloidal humus content may be substantially and greater than the colloidal clay content. And humus make an even greater contribution to the nutrient reservoir. So okay, this is the example of carbonaceous organism. I mean residue. Now this that I was mentioned. So the mycorrhizae or the mycorrhiza are formed of mutualism and association in which both partners derive benefits to the soil and the root system of a plant. Next. Okay, so colloids presents a large negatively charged surface area. So the colloids present a large specific surface area, and the colloid surface carry a large number of charges. Okay, so the function of the colloidal soil fraction as a nutrient reservoir depends on two factors. So this is the two factors. One is the colloids present large specific area, and the other is the colloidal surface carry a large number of charges. Factors have the ability to retain and exchange cations on colloidal surface in the single most important property of soil. And for example, a cube with a mass of 1 gram that measures 10 millimeter on a side. The specific surface area of this cube is 600 millimeter. So that will also subdivided into particles of colloidal dimension. Say it's called the specific surface area. The colloidal surface carry large number of capacity or the charge. The large number of charge of the colloidal surfaces. Colloidal clays consist primarily of aluminum silicates. So this chemical formula for kaolinite, one of the surface clay. This picture is the sample on mass of a cube, which 1 gram that measure 10 millimeter on a side. Then specific surface area of this cube is 600 millimeter. Okay, so these particles of colloidal dimension have high surface area per unit or specific surface area. So this is the example of the factors, which is the colloids present large specific surface and large number of charge. charges. Soil colloids reversibly adsorb cations from the soil solution. So adsorb means absorption. The atoms enter into bulk phase of a liquid or solid, whereas adsorption is the substances adhere to the surface of the molecule. Leutropic series. So this association of cations, positively charged ions, with negatively charged colloidal surfaces depends on electrostatic interaction. So hence, binding affinity varies according to the leutropic series. So static interaction. Okay. So this is the example of electrostatic attraction. Okay. So the two objects in each other's vicinity have different electrical charges. So an electrostatic field exists between them. So negatively charged, for the object, it's negatively charged if it has excess of electrons. So an object is positively charged if it is deficient in electrons. So this is the example of attraction, electrostatic attraction. The positive and the negative ions bind together. So this example is the series of aluminum ions have the highest binding affinity and sodium ions the least, reflecting the general rule that trivalent ions or the three positive are retained more strongly than divalent ions or the two positive, and divalent ions have strongly than monovalent ions or one positive. Ions are also hydrated, which means that they are surrounded by shells or water molecules. And electrostatic rules are modulated by the relative hydrated size of ions. Related hydrated of ions is defined as the radius of ion and closely bound water molecules. So the ions with bigger size and low charge hold water molecule less tightly and thus have a smaller atomic radius. So this is the hydrated or the hydrated size of the ion. Okay. Attraction. The next is the repulsion. So if the negative and negatively charged ions, it will not attract. So rather they will just repulse. So this is the example of electrostatic repulsion. The negative and negative ions. Next is the example of the positive and positively charged ions. So it will not attract, hence it just moving away to each other. Okay. The anion exchange capacity of soil colloids is relatively low. So the soil colloids are predominantly negatively charged, and consequently, they do not tend to attract negatively charged anions. So although some of the clay minerals do contain cations, such as this example, salt, are not held in the soil but tend to be readily leached out by percolating on water. So this is the anion exchange capacity of soil colloids is relatively low. Okay, summary, the uptake of nutrient salts by plants involves a complex interaction between plants, roots, and the soil. So the colloidal components of soil consisting of clay particles and humus present a highly specific surface area carrying numerous primarily negative charges. So ion adsorb to the charged colloidal surfaces represent the principal reservoir of nutrients for the plant. As ions are taken up from the soil solution by the roots, they are replaced by exchangeable ion forms, the colloidal reservoir. So this is the topic, no? Soil. So, thank you.
The minerals in the soil are either in absorbed form or in dissolved form. So to absorb the minerals from the soil, plants use their roots, so as their leaves. Plants take up mineral nutrients in the form of ions. This uptake of minerals can either be passive process, termed as passive transport, which occurs along the concentration gradient, thus requiring no energy, or active process, termed as active transport, which requires energy because it occurs against the concentration gradient. The passive process or passive transport can be explained by diffusion theory, ionic exchange theory, and Jonan's equilibrium. Diffusion theory. When the concentration of mineral ions is higher in the external soil solution than the roots, then the ions in the soil solution will move from a region of a higher concentration to a region of lower concentration. This movement of molecules or ions is called diffusion. There are two types of diffusion: simple diffusion and facilitated diffusion. In simple diffusion, the molecules move from high concentration to a low concentration without a protein channel or without any help at all. These certain molecules can move directly across the cell membrane and it doesn't need help at all. It can walk right through the walls. In this example, we've got a bunch of mineral ions in the external soil solution and few mineral ions inside the root cell. So, the natural tendency of these mineral ions is going to go from the high concentrated area to the low concentrated area. The ions keep moving until equilibrium is reached. One of the reasons that allows the ions to diffuse into the root is because of the apparent free space, or the AFS. Almost certainly, the AFS stops at the endodermis, where in most roots, the radial and transverse walls develop characteristic thickenings called the Casparian band or the Casparian strip. The Casparian band is principally composed of a complex mixture of hydrophobic, long-chain fatty acids and alcohols called sorbitol. These hydrophobic substances impregnate the cell wall, filling in the spaces between the cellulose microfibrils. They are, in addition, strongly attached to the plasma membrane of the endodermal cells. The hydrophobic, space-filling nature of the Casparian band, along with its attachment to the membrane, greatly reduces the possibility that ions or small hydrophilic molecules can pass between the cortex and still without first entering the simplex. This means, of course, that they must pass through the plasma membrane of the cortical or endodermal cells and are consequently subject to all of the control and selectivity normally associated with membranes. This diagram shows the radial paths of ion movement through a root. Arrows indicate the alternative paths that may be taken by nutrient ions as they move from the soil solution into the vascular elements in the steel. Arrows with circles indicate active transport of ions across plasma membranes. Facilitated diffusion. Unlike non-charged molecules, ions will have difficulty to pass through the hydrophilic membrane directly. To facilitate the movement, the proteins called channel proteins and carrier proteins are needed. Ionic exchange theory. In this process, the ions, mainly cations that were absorbed to the root surface due to the negative charge of the cell wall, are exchanged with the ions present in the soil. The positively charged hydrogen ions absorbed into the surface of the roots can easily be exchanged with cations of sodium and potassium present in the soil. Similarly, an ion like hydroxyl ion from the root cell can be exchanged with an ion present in the soil. Ion exchange can be explained by contact exchange theory. According to this theory, ions can be taken up by plants without being dissolved in soil. The ions absorb down to the root surface and the ions attached to the clay particles are not static. They oscillate in a small volume of space. And if the roots of the plant and the soil particle are in close proximity, ion exchange theory can take place. They exchange ions into the roots by diffusion. Carbon exchange theory. Roots of the plants continuously respire, which results in production of carbon dioxide. Carbon dioxide produced during respiration in roots combines with water to form carbonic acid, which dissociates into hydrogen and bicarbonate ions. The hydrogen ions produced as a result are exchanged with cations in soil. Donan's equilibrium. Another theory of passive absorption, which states that there are some ions inside the root cells that are indiffusible across the membrane due to the selective nature of the cell membrane. If the root cell have cation accumulated inside as indiffusible ions, then anions present in soil into the membrane without expenditure of energy to maintain a balanced electrical potential. The movement of an ion in this example will result in an equilibrium which may not be equal in terms of concentration. These mechanics enable plants to take up minerals from the soil to ensure proper growth. Generally, the mineral ion concentration inside the cell can be higher than the solution surrounding the soil. In this case, the ions move against the concentration gradient, that is, from lower concentration to higher concentration. This movement is termed as active transport and requires energy. Active process or active transport can be explained by two theories. According to this theory, the movement of ions across a membrane is mediated by special carrier molecules present in the membrane. These carrier molecules are usually proteins, but they can also be cytochrome, lecithin. Generally, carrier molecule works by binding ions to the carrier molecule and forms a carrier ion complex, causing a change in the conformation of the carrier molecule. The carrier ion complex passes through the membrane. When it reaches the inner side of the membrane, the carrier molecule changes its conformation and releases the ion. After the release of ion, the carrier moves back to the inner surface of the membrane to bind another ion. The binding of ion and its release both require energy, which is provided by ATP. Electrochemical gradient hypothesis. An electrochemical gradient exists across the plasma membrane of the cells. This is due to two things. 1. Splitting of water molecules into hydrogen and hydroxyl ions. 2. The conversion of ATP into ADP and PI in organic phosphate. The proton pumps in plasma membrane pump out hydrogen ion, while hydroxyl ions stay inside the cell, giving inside of the cell a negative charge. The proton concentration increases outside the cell than inside, generating a proton motive force. The electrical and proton gradient established as a result drive anion and cation uptake. Anions from outside of the cell exchange with hydroxyl ions inside the cell, while the cations move inside the cell via ATPase. ATPase configuration changes. It then transports the cation into the cell and changes back its configuration to by another cation. This process is aided by the hydrolysis of ATP.